My name is Kyle Barron. I work at Foursquare, and today I'm going to talk about GeoArrow and GeoParquet in deck.gl. So the goal that's motivating this talk is really, is it possible to get better performance in deck.gl with analytical data sets, and also at the same time, make it simpler for end users? So at a high level, if a user wants to render a web map, there's three overarching themes. You have to get the data into the browser somehow from some external resource. You have to handle that data in memory. And then eventually you have to render that data onto a map somehow. And there's three great tools to work with this. We're all here, we love deck.gl. Deck.gl is amazing for handling this GPU management and doing the map rendering of all this data. But I think that GeoArrow and GeoParquet really fit into these other two steps of handling this data in memory in JavaScript and getting the data into the browser in the first place. So I want to start with deck.gl to motivate why GeoArrow and GeoParquet make sense. So deck.gl has a great performance guide in the documentation that has recommendations for how to make the most out of deck.gl's performance. There's really three recommendations in that document. One is just to minimize how much data you're rendering and how often you need to render it. The second is that if you have functions that deck.gl calls, these accessors, those should be really efficient and use as little CPU as possible. And then the third is to provide binary input into deck.gl. By default, deck.gl works on JSON objects, but it also supports this binary API to provide pure buffers into deck.gl. So the core issue, I believe, here is that the binary input API is super, super efficient, but it's kind of hard to use. Users have to construct these arrays by hand. They have to manage how they load that data, how they handle that data. And then if they have malformed buffers, sometimes it doesn't look very good in deck.gl if the data is slightly invalid. This is a slide from the technical deep dive presentation linked on the deck.gl website. And this describes eventually how deck.gl copies the data onto the GPU. So look at instance positions. That's the attribute that describes where these points should be rendered on the globe. And if you look at the buffer layout, the buffer layout has all the data of the geometry column in a single buffer, and then all the data of point radiuses. And so this is a columnar layout. It has all the data of each column in contiguous memory. So if only there was a cross-language implementation of columnar memory that could help us with these buffer layouts. And of course that exists. This is Apache Arrow. Yeah, we're very lucky. So Apache Arrow is a language-independent columnar memory format. It describes a format that any language can implement that isn't tied to any particular language. And the big goal of Apache Arrow is to enable really seamless data interchange. So outside the browser, for example, Python and C++ and Rust and different languages can use the same memory, even if some other process created that Arrow memory. So it makes it really efficient. And there's a huge ecosystem around this. So there's 11 implementations now of the Arrow specification in JavaScript, Python, several other languages. And there's more and more data frame tools that users are already using that integrate with Apache Arrow. For example, this week, the Pandas release, which is the most popular data frame library in Python, added support for, instead of using NumPy as the data format, you can now use Arrow memory as the format that Pandas is using. So on the right, you can see an arrow table that has some metadata about what is in each column. At the smallest level, you have a column chunk, which is each part of the contiguous buffer. They're batched into record batches, so you can handle a chunked array instead of having to have huge buffers that can't be split up at all. So next, what is GeoArrow? So GeoArrow is it's the specification for how to store geospatial data inside Apache Arrow memory. The core thing here is that GeoArrow is not expanding Arrow in some way. It's operating within the type system that Arrow already defines, which means that if we create GeoArrow data, it can be handled in non-spatial Arrow tools in all of the existing ecosystem. But by defining the specific format, like Arrow's big selling point is that it can be interchanged and exchanged between programs really easily. If all geospatial data in Arrow uses the same format, we can share that data really easily too. So because of this ecosystem that's also growing with GeoArrow, so GDAL 3.5 and GeoPandas are a couple of the tools that have some support for GeoArrow. It makes it easy for users using what are probably their existing tools to get data into GeoArrow. I want to dig a little deep into how does GeoArrow actually represent these geometry types. So the cool thing is that Arrow defines nested types as well as primitive types like integers and floats. So here, this has a logical layout of a fixed size list where each individual list item has 2 values. So on the top right, you can see this logical layout, which is exactly the same as an array of GeoJSON point coordinates. So it's really, the high level API is pretty easy to understand if you're familiar with GeoJSON. But that's not how Arrow actually stores the data at a low level in its buffers. The physical layout is a contiguous array of all of these data points lined up to each other. And crucially, Arrow's APIs provide access to both of these. So if a user wants to understand what's their 10th coordinate, they can really easily access that using the Arrow API. But a program that's performance focused and understands the Arrow buffers can access the really efficient physical storage type really fast as well. Next, let's look at something a little bit more complex. How do you store polygons? Polygons have a level of nesting that's also similar logically to what GeoJSON looks like. So you have an array of geometries, an array of rings, array of coordinates. This is the same as if you had a list of GeoJSON polygon coordinates. Similarly, there is an efficient physical representation for how these polygons are stored in memory. So you have this flat array of coordinates, just like that point buffer, but you also have an index, 2 index arrays. So the first index array in the middle describes where does each polygon ring start. So if you have an index array that's 0, 5, 12, 19, that's saying that the first ring starts at the 0th coordinate and goes until the 5th coordinate. And the second ring goes from the 5th up to the 12th and so on. This means that you can infer efficiently what are the coordinates that map to each polygon. And similarly, you have a geometry index array, which is how many rings does each geometry have. So 0 to 1 means that the first geometry has 1 ring. 1 to 3 means that the second geometry has 2 rings. And those 2 rings go from the 5th to the 19th coordinate. So by looking into each array, you can construct a picture of what that polygon looks like. The exciting thing is that this layout is very close to what deck.gl's binary API uses. So it's exciting because this GeoArrow format that is easy for users to create is also really, really efficient to use in deck.gl. So instead of using something like GeoJSON, where each individual JavaScript array is a small object in the JavaScript garbage collector and has some overhead, and where you need some memory copies to copy that JSON into the binary buffers, you can just handle these binary buffers directly. And so here are 4 layers that work pretty well with these GeoArrow memory layouts. So the scatter plot layer renders points, and you can basically just pass in that point buffer, and deck.gl will handle it really efficiently. And even something complex like the trips layer that renders animated trips of moving vehicles, for example, you can pass in GeoArrow line string geometries, and then a separate arrow column with columnar timestamps where each timestamp maps to one coordinate, and it works really well in deck.gl. So now I want to look at, we have this great format that's really efficient to use in deck.gl, but how do we get this into the browser? And is there a better way than just loading GeoArrow directly? So with web applications, I really believe that bandwidth is the limiting factor for how much data is easily accessible from a user's machine. No matter the GPU and CPU they have, if their internet is slow, it's going to feel like a slow application if you're waiting a minute to download some data. So there's really 3 techniques for making your application feel faster with large data. You can compress your downloads efficiently. If you spend a bit more time on the server compressing data and a bit more time on the client decoding data, that's worth the extra time because the download size might be so much smaller. You can also just need less data. So tiling and spatial filtering are really effective techniques here. One note on the tiling is that vector tiles are a great visualization format, but here I'm focused on analytic data that can also be operated on as their original representation in the browser. And so tiling is great for visualization, but if you want to operate on polygons that cross tile boundaries, that's a lot harder to work on in the browser compared with having the entire polygon geometry at your fingertips. Streaming downloads are also really helpful because if you have a 100 megabyte file, you don't want to wait 30, 40 seconds while your user wonders what's happening before you show anything. So it feels responsive if you can render something before that entire download has finished. So keep those in the back of your mind, but let's look at the Apache Parquet format. So Apache Parquet is a columnar file format, which the main thing to keep in mind as the difference between Arrow and Parquet is that Arrow is designed as an in-memory format that is operated on by the program directly, whereas Parquet is a file format designed for serialization that's designed for a smaller file size, but that needs to be serialized and deserialized before it can be worked with in memory. So for example, Parquet in each of these column chunks has compression, which Arrow does not as its internal format. The cool thing is that even though Parquet started before Arrow, it's broadly interoperable with the types that Arrow provides. So there's a mapping really between every Parquet type and every Arrow type. So when you load Parquet, you can convert that to Arrow really effectively. There's also a really big ecosystem of Parquet. There's core implementations in C++ and Rust and Java, and some high-level bindings as well. But there's also just a huge ecosystem of tools out there that are already using Apache Arrow. So some big cloud data warehouses are using Apache Parquet as their input and export formats. It's integrated in almost every data science analytic tool, like pandas and other data frame libraries. So it's really easy for users to use this with a lot of their existing tools. And because most of the Parquet implementations are developed jointly with the Arrow implementations, when you load a Parquet table, you get an Arrow table automatically. And as a note, that Parquet layout over there is almost exactly the same as the arrow and memory layout. It's also chunked. And so you don't need to read the entire file to understand part of it. So Parquet is a really complex specification. It has lots of different compressions and encodings. There have been attempts at pure JavaScript implementations of Parquet, but they've by and large been abandoned. So in the winter, I started hacking on WebAssembly bindings to the Rust Parquet library, and by now they seem to be working pretty well. So I have this repository that is efficient for decoding and writing Parquet from the browser. And even these bundle sizes are not huge compared to the size of the data that you might be saving by using Parquet. So you can choose which compression codecs to include in the bundle. But even if you include all compressions, it's still under a megabyte when the WASM is compressed itself. Now, looking at GeoParquet, just as GeoArrow describes how to save data in Arrow, GeoParquet describes how to store data in the Parquet format. It's not extending Parquet, just like GeoArrow is not extending Arrow. It's within the existing type system. How do you save this data? Right now, the spec defines WKB buffers as something that's broadly interoperable. But in the future, once the Arrow native encoding that I described at the beginning is stable, that encoding will probably be supported in GeoParquet as well. And so once that happens, just loading GeoParquet with any Parquet library will automatically give you these GeoArrow buffers. The GeoParquet ecosystem is also expanding. GeoPandas and GDAL as of 3.5 handle the GeoParquet format. And we hope that some of these in the future will be adding GeoParquet support to their tools. So the goal is to make it really easy for users to create GeoParquet. Now, looking back at that slide a couple slides ago of how to make your big data website more effective. So compression was that first bit. Parquet supports not only different compression methods, but different encoding methods to make the most of the compression. So run length encoding and delta encoding are supported in Parquet to try and get the most out of these compression options. There's a few different compression options. Some of them are more or less supported in different implementations. But broadly, GeoParquet is way smaller than GeoArrow. And even if you apply gzip to the entire GeoArrow file, GeoParquet is usually a bit smaller as well. But when you compress the entire GeoArrow buffer, you can no longer look inside it. The difference is that GeoParquet, you can look inside it and not need to download the entire file. So here, if you want to actually need less data, you can see that Parquet includes a footer with metadata. So once you load that metadata, you can, that describes the byte ranges of every column in the Parquet file. So after you've loaded that metadata, you can pick out any geometry column chunk in the file and just load that, and it'll work really efficiently. There's also statistics in the metadata about, we can figure out how to get spatial regions encoded into the column chunk metadata. And so a user in the future should be able to pass in some bounding box query and then use that with the metadata to only load the portions of a big Parquet file without having to load the entire Parquet file from the server. And so this is really exciting for big Parquet data sets in the future. And then last was streaming, rendering something before the entire data set has finished downloading. Now, generally stream means you start at the beginning of the file, you can't go backwards or forwards. And so Parquet can't actually be read like that because the metadata is at the end. But you can still use HTTP range requests to handle this. So first, you can read the metadata at the end. You can understand where the byte ranges are of the columns that you care about. And then you can asynchronously load the first record batch, render that in deck.gl, and then render each deck.gl layer as each record batch comes into your application. Then I want to get into a couple examples of using this. So this is 3.2 million points rendered in deck.gl using GeoArrow. There's also, this is in a notebook, an observable notebook. So if you're curious, you can just load this notebook and see this in your browser. So first, we import these two libraries, the Apache Arrow bindings in JavaScript and this WebAssembly Parquet implementation. Here, this assumes we already have the Parquet buffer in memory. There's beta support for asynchronously reading portions of the Parquet file, but here, to make it simple, we just parse the entire buffer at once. And with 2 lines, we can get an Arrow JavaScript table object. So then here, this is a point column in the geometry table. So all we have to do is access that geometry column and then access the raw typed array values that are underlying this column. And so here, this flat coordinate array is that flat point buffer that we saw before. Then this is the deck.gl binary API. So we pass the length of the entire number of rows in the table, and we pass this buffer as the get position attribute. We pass that into the scatter plot layer, and that's it. You have to pass some styling information that's omitted for simplicity, but it's really not that much code to get GeoArrow working in deck.gl. And here's a bit of a GIF. There's so many points that at the lowest level, you can't even really see them. And then at the end, that is 3.2 million points in your deck.gl rendering. And we're closer to having the GPU be the bottleneck and not the CPU or memory be the bottleneck. Similarly, this is an example with polygons. So this is 7 million polygon coordinates across 1 million polygons. This is the Microsoft AI generated US buildings data set for the state of Utah. Similarly, this assumes that we've already loaded the Parquet table into an Arrow table. So here, this is the geometry column for the Arrow table. Then if you remember, there's those 3 buffers that GeoArrow uses for the polygon representation. So the polygon indices, which are the indexes within each ring that each polygon starts at. You have the ring indices, which are the indexes into the coordinate array that each ring index starts at. And then you have that coordinate array, which is the flat array of all the buffers for the entire column. There is one step here that we have to do extra because in Arrow, the polygon indices point into the ring indices, and deck.gl expects the polygon indices to point into the coordinate array. So we do have to perform the lookup between these 2 arrays, but that takes like 10 or 20 milliseconds. And then we can just pass this data into the solid polygon layer, and that's it. So here, this data, we need the indexes where each polygon starts, we need the total length of the number of geometries, and we need the coordinate array. But that's all the information that we need, and that's all provided really by GeoArrow. Here, we also know GeoParquet, you can set the winding order of the polygons. And so we already knew that for this data set that it had counterclockwise winding order. And similarly, it's just so much data right at your fingertips that it's pretty exciting. Although in Utah, outside of Salt Lake City, there's nothing. So what next? These specifications are not yet 1.0, so it doesn't quite make sense to, or there, you know, we don't want to build too much on the pre 1.0 versions if we can't change it. So there's a couple different ways we can go from here in the short and medium and long terms. In the short term, some documentation potentially just for using this with deck.gl. Like these notebooks hopefully are instructional. In the future, we could add this potentially as a helper module to make it really easy for users. We could even add this support to PyDeck to make it really efficient, because Python tools really work well with the arrow format. And so potentially we can pass this data from Python to JavaScript to the GPU really efficiently without needing copies really on the JavaScript side. And that's it. So yeah, thanks for having me. That's good. Any questions?
Can you explain why the Parquet format has the metadata at the bottom?
Why does the Parquet format have the metadata at the bottom? I think it's so that you can start writing. So the metadata includes all the byte offsets for the entire file. And so otherwise you would have to know how big each column will end up being, even after compression, before you've started to write anything, if you put that at the beginning. So making it at the end makes it a lot easier to write. And with HTTP range requests, you can do the ranges from the end of the file. So the last 4 bytes of the Parquet file describe how big the footer metadata is. So you still need a maximum of 2 HTTP requests to have the entire footer metadata. And so it's essentially, for all intents and purposes, the same as if it were at the beginning of the file, where you might not have had the entire metadata in your first request. Does that make sense?
It's pretty amazing. I got a couple. So first one, I like. Well, in the demos that you had, how large is the data? I mean, payload. You know, in this case, like the 7 million coordinates.
Be nice to the people on Slack at home. This file, I think, was 40 or 50 megabytes. The point data set, I think this was down to like 32 megabytes. Each of these data sets only includes geometry for this demo, so that doesn't include any attributes that you want to load in. But like these are 30 megabytes is not crazy for an interactive demo application.
But then what about combining them? About kind of like the idea of like, it's, I mean, like, yeah, 30 maybe is not, but then you go to 10 times these 32 million points, and now you're in 100 megabytes. So there's going to be always a limit of how much you can do client side, and then you're going to have to start tiling. So have you thought about using kind of like the partition system of Parquet to kind of like create, you know, like tiles and then encode the data within the tiles in the arrow? I mean, essentially tiling this.
I mean, I haven't been looking into the tiling itself. I'm excited about the potential for spatial indexing. So if you have like a very big data set on the server that's partitioned by spatial extent, you could view part of the data set at a time if you have a small spatial extent that you want to view at a time. But I haven't thought much about Parquet plus tiling.
Okay. No, that's definitely, I think, you know, that's something that, you know, like if deck.gl, I mean, like it's all about like handling large data sets and effective visualization of large data sets. I think, you know, that may be an area we're going to need to invest more and, you know, like how to efficiently, like, you know, because 3.2 million points sounds like a lot, but I mean, like as soon as you do 3.2, someone's going to ask for 30 million. You know, it's like you're already stuck in the way. The other one that I have is, you know, it's like, well, you know, we're trying to move with GeoParquet. We've been doing that, have been talking about it. I mean, what is your vision? I mean, like how stable are we, you know, in order, you know, to get to a point of, you know, like stabilizing GeoParquet and even, you know, GeoArrow?
Like how far are we from stabilization? Or, I mean, I think it's pretty difficult to talk about when things will become stable. I mean, there's a lot of great contributors who are creating issues. All of you should look at the specifications online, give us your feedback, tell us what are we doing wrong right now, and how can we make it better. But I'm just excited for more feedback while these specs are still growing.